Hello again, Physics 243. In this unit, we'll discuss thermometers and temperature. So everyone's familiar with temperature. Everybody experiences hot and cold, but it took a really long time to have a scientific understanding of what temperature is. Certainly the first order of business was to be able to measure it. And so thermometers, how did thermometers come about? That's what this unit is about. So as temperature increases, as things get hotter, materials tend to expand. Most materials increase in size, volume, area, or length, depending on how you measure it, with increasing temperature. This has consequences. So here are some train tracks, and if you don't set them up to take this phenomenon into account, then they can buckle like this on really hot days. Happens also with concrete. In streets, there are chunks of concrete that expand, and then if there's no room for them to expand, they start to destroy each other like this. And that is why you see these kinds of spacers, especially on bridges. So bridges are not coupled to the earth so that their temperature changes are quite big. And so you really need these spacers so that this doesn't happen to your bridge. So most things increase in size as they get hotter. So the first order of describing this quantitatively is to think about linear expansion. So here's a rod at temperature T0, length L0, and at some higher temperature T, it's a little bit longer by delta L. First approximation to that is linear. So the length, the elongated length, is equal to the length at temperature T0 times this factor, 1 plus alpha times the change in temperature. So you see if there's no change in temperature, you just get L0 back. Otherwise, you get an increase that increases linearly with temperature. So this is the first approximation. And the number alpha is the coefficient of linear expansion. So it's a number that depends on the material, a characteristic of the material. Volume expansion is similar. This is what's relevant for liquids, gases, and solids. And this is what is observed phenomenologically. So this is the first order of approximation. The change in volume is simply a factor times the original volume. That factor depends linearly on the change in temperature. And then there's a coefficient beta, the coefficient of volume expansion. And again, the beta depends on the material. So there's this chart on page 364 in the book, excuse me, coefficients of expansion near 20 degrees Celsius. And there's a coefficient of linear expansion, this is the alpha, and this is the beta for volume expansion. Here are the formulas. So you can see which ones extend more than others. So lead and aluminum have larger alphas than these other metals. Concrete has like 12. Glass and ordinary glass, especially Pyrex, does not have much, so that's pretty good. That's why you can put hot water into a Pyrex container and it won't shatter. Or it's less likely to shatter than just ordinary glass. Of course, for linear expansion, it doesn't make sense to talk about that for liquids and gases, but for volume expansion it certainly does. And notice that quite high on this list, quite high numerically on this list, is ethyl alcohol at 1,100 10 to the minus 6. And the units are per degree Celsius. Okay. So as temperature increases, materials expand. Other things happen too. Here's one: the color of the radiation shifts. So this is basically light that comes out of something shifts. So this is a phenomenon that we'll be discussing next semester a little bit more. But perhaps you've seen a electric oven, excuse me, electric stove, and the heating element turns bright red if you put it on high, right? You're gonna boil some water on an electric stove, the heating element goes from being this sort of cold black to being this really, really hot red. And in general, as things get hotter, the emitted wavelength from things, the emitted color, as it were, shifts. whole bunch of electrical properties also change with temperature. That'll be discussed again a little bit next semester. And so a bunch of things change, and in general, the amount of change, per degree of temperature change depends on what the material is, as we saw on that chart, previous page. But here's the key of all this. Temperature is quantified by using one of these properties to make a thermometer. So as I was saying, temperature is a mysterious thing for many, many years. But it took until the mid-1700s, early 1700s or so to figure out how to even measure it consistently and accurately. And so the first order of business to make something scientific is to figure out a way to measure it. So you can make temperature measurements by using these properties, this phenomenon. So for example, many thermometers are based on thermal expansion of liquid. So you make a thermometer like this. It's a enclosed glass thing. Here is some red liquid. It's often ethyl alcohol with a little dye, because you saw that had a big number for the volume expansion. And this part of the thermometer is kind of thin, so that if the volume of the fluid increases, then you have a big change in this altitude. All right, so you've seen these thermometers before, right? They're usually outside, so you can see how hot it is. This is a hot day, 100 degrees Fahrenheit. And you've probably seen, I don't know, maybe you've seen a mercury thermometer in the context of like measuring your temperature, check if you have a fever. Nowadays, they're electronic, which is thermometers based on electric properties of things. But there still are mercury thermometers like this. Some thermometers are based on the thermal expansion of solids. So in particular, this is a clever little trick. You can make a bimetallic strip. So you take two metals that have different expansion coefficients and glue them together like this. So there's a green metal and there's a blue metal, and they're glued together. And so when you heat it up, one will expand more than the other, and as a consequence, it'll bend like that. And so sometimes this is used as a switch, because the metal bends and then makes a connection, and then completes a circuit and something happens. You often see this kind of a thermometer for ovens or for cooking, checking temperatures in meat or whatever. See how there's this coil? This coil is a bimetallic strip. And as things get hotter, it expands, and this needle starts to move up. And so it can be calibrated to tell you what the oven temperature is. All right, so thermometers are based on expansion of a solid in this form. Okay, so you can make a thermometer like this, and then you have to kind of put a scale on it, right? And so we're familiar with Celsius and Fahrenheit. This is what's generally used. Celsius is much more common around the world. Fahrenheit is still used here in the United States a lot. So the calibration is as follows. The freezing point of water is 0 degrees Celsius, or 32 degrees, and 32 degrees Fahrenheit. And similarly, the boiling point of water is 100 degrees Celsius, and that's 212 degrees Fahrenheit. So with these 2 points, you can calibrate the scale. For the Celsius, you divide 0 to 100 into 100 pieces, and then for Fahrenheit, there's 180 degrees between 180 degrees between 32 and 212. Okay, where does this come from? Well, Daniel Gabriel Fahrenheit, who lived late 1600s and early 1700s. He was the first one to really do high precision thermometry. He was the first to really develop a way to accurately measure temperatures. And in particular, he invented the mercury thermometer, which is quite accurate and really remained the most accurate way to measure temperatures until basically the late 1800s, early 1900s, so not that long ago, really. He proposed his temperature scale in 1724. His 0 degrees is the temperature at which a mixture of ice, water, and salt in 1:1 ratio is at equilibrium. So that means that it's the temperature at which you have a certain amount of ice, certain amount of water, and then they don't change into each other, mixed with salt. Why? My guess is that because you can do this, you can create this mixture in a laboratory and then recreate this temperature. That's my guess anyway. He put the freezing point of regular water at 30 degrees. Why he chose 30, I don't know, and I'm curious about it. He also put his estimate of body temperature at 90 degrees. So these were calibration points. And interestingly, he had 3 calibration points, which can be problematic. So later, and I'm not exactly sure when, the scale was redefined so that the freezing and boiling point of water are exactly 180 degrees apart. And I should say the freezing point is 32 degrees, as I said in the earlier slide, and the boiling point is 212. So exactly 180 degrees apart. And that's the current Fahrenheit scale. This is the sort of historical background. Celsius. The Celsius scale comes from this gentleman here, Anders Celsius, who was Swedish, predominantly known for his temperature scale, but he was influential astronomer, especially. Anyway, 1742, so sometime after Fahrenheit, he proposed a temperature scale based on dividing the space between the freezing and boiling point of water by 100. Now, curiously, historical note here, he reversed it relative to what we do. His boiling point was at 0 degrees, and the freezing point was at 100 degrees. So on his original Celsius scale, things got colder as the temperature went up. I have no idea why, but it just kind of illustrates that, the positive direction is arbitrary. You can pick it to be whatever you want. Well, almost immediately, J.P. Christian, who was a very influential scientist and leader of a influential scientific organization, reversed the scale. And Linnaeus, who you may recognize from your biology classes, also reversed the scale. So that when temperature increases, the number goes up. Now, until 1948, it was known as the centigrade temperature scale. Centi meaning 1/100th. So that means you break it up into 100. And after 1948, in order to differentiate this name between some other things related to measurement of angles, it was changed to be called the Celsius scale. A couple of interesting things about Mr. Celsius. He was the one that proposed a connection between the aurora and changes in the magnetic field, which turned out to be accurate. He did some of the first non-human eye measurements of the brightness of stars and was involved in an expedition to establish that the Earth is shaped like an ellipsoid, as Isaac Newton had believed. It's sort of fatter at the equator and wider at the equator and flattened at the poles. It's very subtle, but it's true. It's there. Think about why that might be and how it's related to the spinning of the Earth. Anyway, the relationship between the Celsius and Fahrenheit scales. So you can just convert from one to the other, but here's what you can remember to be able to do it. 0 degrees Celsius is 32 degrees Fahrenheit. I think everybody is familiar with that, or usually is familiar with that. Then remember this, 5 degrees Celsius equals 9 degrees Fahrenheit. So kind of a curious conversion, but 5 degrees Celsius is 9 degrees Fahrenheit. And so you can, let's say you start with a temperature in Fahrenheit. To convert to Celsius, the first thing you do is shift it by 32 because of this first fact. And then you just do a unit conversion using the second fact. So multiply it by 5 degrees Celsius divided by 9 degrees Fahrenheit. That cancels the Fahrenheit, and you're left with the Celsius. Right? So this numerator equals that denominator. So it's just a unit conversion. Usually the formula is written in this form with the 5/9 in front. So you have that formula, and then if you want to go from Celsius to Fahrenheit, you can just invert this formula and you get this. Now here's an interesting fact. -40 is the same temperature on both scales. That once came in useful when I was playing trivia. Didn't really win anything, but I won the admiration of my peers. Okay, so that's it for this brief little discussion, introduction to thermometry. Next up, we'll talk about the behavior of gases. See you then.